All right, so you ready to dive in? This time, we're cracking open Professor Ramesh Dongana's Birth of Astronomy.
Oh, cool.
Yeah, chapter 2 specifically.
I like it.
Have you ever thought about, how we even figured out Earth is round?
Yeah.
Or what really convinced people that the sun, not the Earth, is the center of, everything?
Right, right.
This chapter totally unpacks all that, and that's exactly where we're headed today.
Awesome.
So get ready. We're going to map the sky, old school style, with this thing called the celestial sphere. We'll dig into that weird wobble the Earth's axis does, and get this, unpack how some dude back in ancient Greece basically measured the entire planet, using shadows. Oh, and we got to talk about that epic battle, Earth-centered folks versus the sun-centered crew.
Right, that's a big one.
Yeah, a real cosmic showdown. And to help us navigate all this, we've got an expert who can connect the dots and show us the so-whats of it all.
Well, I'm excited to see how these early observations and ideas, how they kind of set the stage for, everything we know today about the universe.
For sure. So the chapter starts off with this idea of the celestial sphere.
Okay.
It sounds kind of like sci-fi, right?
It does.
But it's actually pretty straightforward, isn't it?
Yeah, it is. Think of it like this giant imaginary sphere, you know, surrounding the Earth like a backdrop where all the stars are projected.
Oh, I see.
So instead of just looking up and seeing a random jumble of stars, it gives us this framework, this celestial map to kind of visualize where the stars are and how they move, at least from our view here on Earth.
Oh, that's smart. So instead of chaos, we get this sphere, and it helps us make sense of what we're seeing. Clever.
Exactly. And to make it even more useful, they added these key components like the celestial poles and the celestial equator.
Wait, so just like Earth has, a north and south pole and an equator, the celestial sphere does too.
Exactly. Picture this. The celestial poles, they're basically if you took Earth's axis and extended it way out to touch this sphere.
Gotcha.
And then the celestial equator, that's just Earth's equator, projected outwards. It divides the sphere into, you guessed it, northern and southern hemispheres.
Whoa, mirroring our own planet.
Yep, exactly like that.
Okay, this is starting to click for me, how this sphere helps us track the stars. But what about those celestial coordinates I read about? Declination, right, ascension. Are those kind of like space latitude and longitude?
That's actually a great analogy. Declination, it's like latitude, measures how far north or south a star is from the celestial equator. And right ascension, that's our longitude, measures the angular distance eastward along that equator.
I'm with you.
So together, they give each star a unique address.
Oh, the cosmic GPS coordinates.
Yeah, so astronomers can pinpoint their exact spot.
That's pretty cool. So using this whole sphere and coordinate system, astronomers could make really detailed maps of the night sky, kind of like how we use GPS to navigate here on Earth.
It's the same idea, and that's the beauty of it. It gave everyone this common language to understand where stars are and how they move. Plus, it helps explain why some stars seem to move across the sky while others, they just stay put.
Right, I've always been fascinated by how Polaris, the North Star, just seemed to hang there while everything else is rising and setting.
It's all thanks to Earth's rotation. Stars near those celestial poles, they seem to circle around them.
Okay.
While stars further away, they trace these bigger arcs across the sky, rising in the east, setting in the west, that whole thing.
Man, I never knew there was so much going on up there. So way more dynamic than it looks.
It definitely is. And speaking of dynamic, we got to talk about Earth's axial precession, that wobble you mentioned earlier.
Oh, yeah. Okay, so here's where things get really interesting. I always pictured Earth's axis as this totally steady thing. But turns out it kind of does its own thing, doesn't it?
You could say that. So Earth's axis, it doesn't just spin, it also wobbles slowly over time, kind of like a spinning top. It takes about 26,000 years for one full wobble.
Wait, are you serious? So that means the North Star won't always be Polaris.
You got it. Because of this wobble, different stars get their turn to be the North Star.
Wow.
Over this super long precession cycle. Imagine looking up thousands of years ago, totally different star marking that north celestial pole.
That just blows my mind.
Yeah.
So the night sky isn't as fixed as we think?
Nope.
What we see is just a snapshot in time. Over long periods, things change big time.
Absolutely. And it's not just about the North Star. This wobble, it also affects which constellations we can see throughout the year, and even from different spots on Earth over those like super long timescales.
Yeah.
It's like this constant slow dance of the cosmos.
It really makes you appreciate, like, the vastness of time. You know, and how the universe is always changing.
For sure, for sure. I bet this was a pretty big revelation for those early astronomers.
Yeah.
Adding, another layer of complexity to what they thought they knew.
Makes sense. And speaking of revelations, let's talk about Eratosthenes, right? That guy who figured out how to measure the Earth's circumference, like way back in ancient Greece.
Oh, yeah, he was brilliant.
He was a total genius. What was it? Just shadows and some simple math.
It really shows you what you can do with keen observation and logic.
Yeah.
So Eratosthenes, he noticed this thing on the summer solstice at noon. The angle of the sun's rays was different in two places, Alexandria and Syene. In Syene, sun was straight overhead, shining right down a well, no shadow.
Right.
But in Alexandria, further north, the sun cast a shadow at a measurable angle. He knew the distance between the two cities.
Yeah.
And he figured out this difference in angles. It was all because of Earth's curvature.
So he's comparing these shadow angles in two spots, knows the distance between them.
Right.
And basically uses geometry to figure out the Earth's circumference. I mean, that's incredible.
It is. And the thing is, he got a pretty accurate measurement, especially for back then, considering the tools they had. It's amazing what human ingenuity can do, just like simple, elegant science.
Imagine this. You're in some city 500 miles north of where the sun's directly overhead at noon, right? You measure the sun's angle, and it's 7 degrees off from vertical.
Okay.
Could you, using Eratosthenes' method, figure out Earth's circumference? It's a fun little challenge.
Yeah.
Shows you how, like, a few observations can unlock huge knowledge about our planet.
It's a great way to, like, step into the shoes of those ancient astronomers and really appreciate their methods. And the cool thing is, understanding Earth's size, that played a big role in how they started to picture the universe as a whole.
Oh, I bet.
Yeah.
So I guess that's where we'll pick up next time?
Yeah, let's dive into that.
Okay, so we've got this picture of Earth, right? Like this sphere just cruising through space.
Right.
But for forever, people thought Earth was the center of everything, with, the sun, the stars, all revolving around. That's that geocentric model, yeah.
Yeah, that's it. And it kind of makes sense, right? Think about it. From where we stand on Earth,
Right.
it totally looks like everything else is moving around us.
Yeah. The sun comes up in the east, sets in the west.
Exactly.
The stars seem to circle overhead.
It just feels natural to think that way, especially, way back then, before telescopes and stuff.
Totally.
Yeah.
Plus, it's like it just made sense intuitively, I guess.
Right. And the geocentric view, it had some big names backing it up, too, like Aristotle, Ptolemy.
Oh, yeah, those guys.
Their ideas, they were like the gold standard for centuries.
Making sense for the time.
And it fit with those religious beliefs, Earth and humans at the center of creation, the whole thing.
Right. But then, bam, this totally radical idea pops up. The heliocentric model,
Yep.
putting the sun, not Earth, at the center.
Big shift.
Huge. What even made people start thinking that way?
It was a slow burn, for sure, with a few, brave thinkers challenging what everyone assumed.
Yeah.
There was this Greek astronomer, Aristarchus of Samos.
Okay.
He actually proposed a heliocentric model way back, 3rd century BCE.
No way. He was that far ahead of everyone else.
Yeah.
But if it was such a good idea,
Yeah.
why didn't it catch on back then?
Well, remember, the geocentric model, it worked based on what people could observe.
Yeah, true.
And it fit those, philosophical and religious views.
Right.
It wasn't easy going against that. It took centuries for things to change.
So who finally brought this heliocentric model into the, mainstream? Made it, the accepted idea?
That would be Nicholas Copernicus in the 16th century. He wrote this whole detailed heliocentric model.
Okay.
And it offered a way simpler explanation for, how planets move.
Interesting.
It sparked some serious debate, but it also, planted the seed for a whole new way of understanding the cosmos.
It's crazy how ideas can just, simmer for ages.
Yeah.
And then, boom, they change everything.
Totally.
Yeah.
And that's exactly what happened with this heliocentric model. It wasn't overnight. Even after Copernicus, there was pushback.
People didn't want to give up the old view.
Right. It took more evidence and other astronomers to really solidify, the sun-centered view.
Okay, so One of those guys was Johannes Kepler, right?
Oh, absolutely.
Took Copernicus's idea and, like, ran with it.
Yep, yep. He came up with his famous laws of planetary motion.
He was a serious math whiz, right? And used all those observations from Tycho Brahe.
Oh, yeah. Kepler was brilliant, a total math and astronomy geek. And using all that data from Brahe, super detailed stuff,
Yeah.
he was able to figure out the real deal about how planets orbit.
Okay, so what'd he discover? Break it down for us.
All right, so his first law, it says that planets don't actually move in perfect circles around the sun.
Oh, really?
Nope. They travel in these elliptical paths with the sun at one of the, whatchamacallit.
Oh, the foci, right, of the
It's
ellipse.
one. Yeah, so their orbits, they're like stretched out circles.
Kind of oval-shaped.
Exactly. And then his second law, that's about how a planet's speed changes
Okay.
as it goes around the sun.
Makes sense.
It speeds up when it's closer to the sun and slows down when it's further away.
Huh. I wouldn't have guessed that. You'd think it'd just be a steady pace.
Right. But Kepler's laws, they showed us it's way more complex than that.
Yeah.
And then there's his third law. This one's a bit more,
Mathy.
yeah, that's the word. It's all about the relationship between a planet's orbital period, so the time it takes to go around the sun once,
Okay.
and its average distance from the sun.
So there's like a pattern there. The farther away a planet is, the
Yeah.
longer it takes to orbit.
Exactly. Kepler's laws, they weren't just descriptions. They were like predictive tools.
Oh, wow.
They let astronomers figure out where planets would be.
Really precise, huh?
Yeah, incredibly accurate. And that was huge for proving the heliocentric model. Really cemented it as like the correct way to understand the solar system.
It's wild how, like, each of these scientists built on what the others had figured out
It's amazing.
to get this, like, complete picture of how planets move.
It's a real testament to human collaboration.
Yeah, yeah. But we can't talk about all this without mentioning Galileo
Oh, of course not.
and his telescope.
Superior.
Like, he opened up this whole new way of seeing the universe, right?
Absolutely. Galileo's work, game changer. One of the first to point a telescope up at the sky.
And what he saw, it shook things up big time.
Oh, yeah, he challenged centuries of, like, accepted knowledge. Pivotal moment in astronomy.
So what exactly did he see that caused, such a stir?
One of the biggest things. The phases of Venus.
Like how our moon has phases.
Yeah, just like that. He saw that Venus goes through a full cycle of phases, from a thin crescent to full and back again.
Okay, but why was that such a big deal? Why did that matter so much?
Well, think about it. If Venus went around the Earth,
Like the old model said.
exactly, then we would only ever see certain phases, not the whole set. To see all those phases, Venus has got to be orbiting the sun, so it gets lit up from different angles, from our perspective here on Earth.
Oh, I see. So Galileo's observations, they were like direct proof that Venus orbits the sun.
Exactly. It was huge. For backing up that heliocentric model, really tipped the scales.
And that wasn't all he found, was it?
Nope, not even close. He also saw these tiny little dots orbiting Jupiter.
Wait, are you saying Jupiter has moons?
Oh, yeah.
That's amazing.
That was the first time anyone had seen moons around another planet. Not everything goes around the Earth. Another point for the heliocentric view.
Yeah, Galileo's discoveries, they must really ruffled some feathers, huh? Yeah, I bet. Back then it must have been a huge deal.
Oh, totally. You can imagine, right? Everyone thought they knew how the universe worked.
Ah.
And then Galileo comes along, drops this bomb. It's like their whole worldview gets flipped.
Yeah, especially with the church, right? They were super powerful back then.
Oh, yeah. And Galileo's observations, they directly challenged, all those beliefs about Earth being at the center of it all.
Right. It wasn't just science. It was about, like, who had the authority,
Yeah.
to say what's true about the universe.
Exactly. And unfortunately for Galileo, it caused some serious trouble.
Yeah, he got into a lot of hot water with the church, didn't he?
Oh, yeah. They labeled his ideas as heresy
Wow.
and forced him to, take back what he said, put him under house arrest.
That's a bummer, but it just goes to show that, like, scientific progress, it's not always easy.
Right. Sometimes you got to challenge the status quo, and that can have, consequences.
Yeah. Galileo paid the price, for sure. But, his discoveries, they couldn't just be ignored.
Nope.
It really
Yeah.
paved the way for, like, a whole new way of doing science.
Yeah, where evidence and observation, they became the most important things.
Instead of just, like, accepting what the authorities said.
Right. It's like Galileo said, see for yourself.
Exactly. And it's amazing to think how far we've come since those early days of, just looking up at the sky,
Yeah, from those first simple observations.
to like mapping out the whole celestial sphere, figuring out how planets move.
It's been an incredible journey.
It really has. And what's cool is there's still so much more to learn.
Oh, absolutely. The journey's not over, not by a long shot.
That's what I love about astronomy. It's like there's always a new mystery to solve.
Yeah, and a lot of those discoveries, they build on what these early astronomers figured out.
Right.
Like that celestial sphere we talked about and those coordinates, declination, right ascension.
Yeah.
We still use those today to map out where stars and galaxies are.
Wow. So those early ideas, they're still relevant.
Totally. They were important steps in, like figuring things out, and they still influence how we approach astronomy today.
Like think about Eratosthenes and how he measured the Earth.
Yeah,
It might seem simple now,
right.
but back then it was groundbreaking.
It showed us that you can use like basic observations and logic
Yeah.
to learn these huge things about our planet.
It's like he started this chain reaction of discoveries.
And Galileo, too. His observations, they weren't just about the sun being at the center.
Right.
They changed how we saw celestial objects,
Yeah.
He showed us planets can have moons,
Mm-hmm.
that the sun has spots, the moon has mountains and craters.
Like it wasn't all just perfect spheres up there.
Exactly. The universe was way more dynamic and complex than anyone thought.
Yeah, and his story, it reminds us like to question everything
Yeah.
and be brave enough to challenge, what everyone else believes, even if it gets you into trouble.
Absolutely. Sometimes you got to rock the boat to get to the truth.
And that's what makes science so exciting.
For sure. There's always more to uncover.
Well, on that note, I think we've covered a lot of ground today.
We did. From ancient Greece to Galileo, it's been quite a journey through the history of astronomy.
It really has. Thanks for taking this deep dive with us and, for sharing all your insights.
It's been my pleasure. Always happy to geek out about astronomy.
And to all our listeners, thanks for tuning in. We'll see you next time for another deep dive into the mysteries of the universe.